Math 242, Cuesta College. I'm Joe Vasta, and we are covering section 8.3, Matrix Arithmetic. So, I think we told you already what a matrix is, and we used them when we solved linear systems of three variables. But just again, to remind you, a matrix is a table of numbers. Actually, it doesn't have to be numbers, it could be functions or elements, but it's a table that looks like this. Okay, so we're going to answer some questions about this matrix up here. What are the number of rows? How many rows are there? Rows run horizontal, so there are 2 rows. Well, let's find the number of columns. Columns run vertical, and there are 1, 2, 3, 4 columns. What is the size of this matrix? The size of this matrix is always going to be rows by columns. So this is 2, and then, instead of writing out by, we'll put an X there. 2 by 4. So that is a 2 by 4 matrix. And let's look at a definition here. 2 matrices are equal if they have the same size and their corresponding entries are equal. Wow, look at the way I spelled equal there with an extra U. Wow, I must have been tired when I did that. Or maybe I just can't spell, but I just noticed that as I'm reading it. I put my capital L there. English teachers hate me when I do that. So look at this. We have none of these are not equal because they don't have corresponding entries. I mean, this would have to be equal to that right there, and that's a -2 and that's a 1. And of course, these guys are not equal to C. They don't even have the same size. So let's go ahead and talk about the size of these matrices. What is the size of matrix A? It is 3 by 2. And the size of matrix B is also 3 rows by 2 columns. This one, it's hard to get wrong. The size of that matrix is 2 by 2. Okay, so what are we doing with matrices? We're doing arithmetic. What is arithmetic? Adding, subtracting, multiplying, dividing. And so that's what we're going to do with matrices, except we're not going to do matrix division because it is not defined. At least it's not defined standard in a standard class like this. So we're just going to do adding, subtracting, and some multiplication. So we are going to use those matrices, and we're going to do problems like this. A plus B. Okay, so this is matrix addition. I'm going to go ahead and write down those 2 matrices. So how do we add 2 matrices together? So I write down matrix A, and I add it to matrix B. Now, if you were just coming up with matrix addition on your own, okay, so that's what that equals this. How would you add 2 matrices together? And the answer is most people would say, well, we would add corresponding elements. So we would say we would add this corner, this top left corner with that top left corner, and we'd end up getting 1 plus a -2, which is -1. And we'd get 0 plus a -3 is -3. -1 plus 0 is -1. 6 plus 4 is 10. A lot of arithmetic. 3 plus a -5 is -2. And 9 plus a -7 is +2. So I add those 2 matrices together. I end up getting another matrix. It's smeared there. Okay, that's all right. So let's go ahead and do matrix subtraction. And if we can add 2 matrices, we probably can subtract 2 matrices as well. We'll put a line right here, and we're going to say this A minus B equals, and I'll write out these matrices. A minus B. Okay, so if you were coming up with matrix subtraction, you would also subtract the corresponding elements. So we would go 1 minus a negative 2. So that gives me a 3. Then we'd have 0 minus a negative 3, which is a 3. Negative 1 minus a 0 is negative 1. 6 minus 4 is 2. 3 minus a negative 5 gives me 8. And 9 minus a negative 7, that's 9 plus 7 is 16. There's the answer for A minus B. So we now know how to add two matrices, and we know how to subtract two matrices. We're going to do a few more before we get to the scalar multiplication. We'll do one more before we get to scalar multiplication. Okay, so you can see scalar multiplication on number 4. Okay, A plus C. So A is this right here. 1, 0, negative 1, 6, 3, 9, plus C, 2, 0, 3, 5. Okay, so when we add those together, well, how would we do that? Well, some of you are getting a little upset because those matrices are not the same size. See, this is a 2 by 2 and this is a 3 by 2. So when the matrices are not the same size, okay, so the sizes are different. This will probably happen in your homework, and when that happens, then you say that this is undefined. Your book might say not defined, which means the same thing, so that's undefined. So if you're asked to add or subtract two matrices of different sizes, there's your answer. Scalar multiplication. Okay, so that's weird that we wouldn't say matrix multiplication. Well, we're doing scalar multiplication, which is a number times a matrix, which we can do. Now, we don't have scalar addition. We can't say, like, what is 7 plus A, because that is undefined. Okay, we can't say, like, 7 plus a matrix, but we can go 7 times a matrix. And so let's write that out. 7A is going to be 7 times matrix A, which is 1, 0, negative 1, 6, 3, 9. So if you were just coming up with this on your own, what would your guess be on how you would go 7 times this matrix? Well, a lot of people's guesses would be that you would take every element in this matrix and multiply it by 7. And that's what we're going to do. 7 times 1, 7 times 0. 7 times negative 1 is negative 7. 7 times 6, 42. 7 times 3, 21. And 7 times 9 is 63. And so that's how you do scalar multiplication. Let's go ahead and do another arithmetic problem on the matrices. We'll use those same 3 matrices, A, B, and C. We didn't really use much of C in these problems so far. So here's the next one right here. Negative 2A plus B. So this really means negative 2A plus B. Okay, so we have these matrices written down, and it's important that you copy them down correctly, or there will you'll see some errors enter your work. So sometimes people go, well, let's add those matrices together, but this has the same order of operations that you may have learned in another class. Remember the order of operations. PEMDAS, please excuse my dear Aunt Sally. It just says that you do multiplication and division before you do addition and subtraction. So that's what I'm going to do. I'm going to do -2 times that matrix. So let's see what we get. When we get that, we get -2 times 1, -2 times 0, -2 times -1, -2 times 6, and I'm writing down what those answers are. -2 times 3, and -2 times 9. And I'm going to add this to this matrix here. -2, -3, 0, 4, -5, -7. Okay. So now all I have to do is add those two matrices together. And when I do, I end up getting -2 plus a -2, which is -4. I get 0 plus a -3, which is -3. 2 plus 0. -12 plus a 4 is -8. -6 plus a -5 is -11. And the -18 plus a -7 is -25. That completes problem number 5. So really, we've done worse things in this class. I've got to say this is not the worst thing we've done. Let's go do our next example, which is problem number 6. We'll move this paper here so we can see A, B, and C. And problem number 6 asks us to go A times B. So we kind of learned our lesson that, you know, maybe we should have same size matrices here when we do our arithmetic. Or maybe, I don't know, this is a new thing, matrix multiplication, which is different from scalar multiplication. Scalar multiplication is a number times a matrix. Matrix multiplication is a matrix times a matrix. So we have 1, 0, -1, 6, 3, 9. Okay, let's continue here. And then the next one, which is B, is -2, -3, 0, 4, -5, -7. Okay, now if you were coming up with these rules on your own, you'd probably say, hey, just multiply corresponding elements. And here's the part that's going to freak you out. This example is undefined. The answer is undefined. You might say, well, why, Joe? What's going on here? This is a 2 by 3, 3 by 2, and this is a 3 by 2. Can't we do it? Well, we have not officially told you how to multiply two matrices together, and that's what we're going to do now with our next example. I'll do that with our next example, and then we'll come back to this example and see why it didn't work. Okay, so I'm going to start the numbering back at number 1 again, and because we're done with that A, B, and C. I'll go back to number 6, but we're kind of done using those. And we want to multiply these two matrices together. Now, this seems like unlikely that we can do this, and it's actually going to be very doable with the way matrix multiplication is defined. Okay, so this is what I'm thinking here. I'm going to use both pins. The first matrix, the matrix on the left, always has this guy called the row runner. He runs across the rows. That will always happen on the matrix on the left. The matrix on the right, this guy right here, is the column dropper. Okay, so he drops down the columns. Row runner, column dropper. This almost reminds a lot of people of the road runner and the coyote who always falls off cliffs. So I will call this guy the road runner and this guy the coyote. And so what I'm going to do is I'm going to start off right here, first row, first column. This is the first column here on that matrix. I'm going to multiply. 1 times 1 is 1. Now I'm going to move these guys over. That's a -5. And then I'm going to move these guys over. Coyote, he's on the ground. It's 0 times 2, which is a 0. What am I going to do with these three numbers that I got by multiplying elements of the first row on that matrix with the first column on that matrix? I'm going to add them together. So I'm going to add them together. I'll do that, and I'll get something. Okay, so now we just had the Roadrunner go that way and the Coyote drop down there. Now they're going to go back. The Coyote is going to move over to the next column. He's going to fall off another cliff. So watch this. We'll multiply. 1 times 3 is 3. Of course, I've got to use the Coyote to write the number there. I wish I had 3 hands at this point. And then I move. And then -1 times -2 is a positive 2. And then we have, where were we? Okay, right here. Then we have 0 times 4, which is 0. Okay, so that's where we are. Coyote goes back up. Roadrunner goes back to the front. Coyote's going to go over here. We'll multiply again. 1 times 6. -1 times a -1 is a positive 1. And a 0 times 7 is a 0. Okay. Coyote back up. Roadrunner back to the front. Coyote goes to the last column, and we do the same thing. 1 times 8. -1 times 0. And 0 times -3. Now look where I am. I'm in the first row and the fourth column. This is going to be a matrix right here, and this is the first row, the fourth column. This entry right here, which was gotten from that. Now, we're right here. Roadrunner goes back. Coyote doesn't have any other columns to go to, so the Coyote goes back to the first column, and the Roadrunner now goes down to the second row. So let's do this. We have 4 times 1. I'm going to put that right there, and we'll talk about why that goes there. And then we have 3 times 5. It's 15. And then we have 2 times 2. So where am I? The Roadrunner is in the first. The Roadrunner is in the second row, and the Coyote is in the first column. This entry is second row, first column. Now look at this entry is going to be second row, second column, and that I'm going to go like this: 12 minus 6 plus 8. So I'm not saying the multiplications anymore. I'm just seeing if you can see that that's what that's what's going to happen. Coyote goes back up. Roadrunner goes back. Coyote goes to third column. 4 times 6, so that's 24 minus 3 plus 14. Okay. We go back up, we go over there, and we come over here and we go 32 plus 0. And we have minus 6. Now, we've got to clean up our answer, but we've just multiplied 2 matrices together. And I know what you're thinking. You're thinking, wow, this is completely worthless. We're going to show you some applications that are not so worthless. So I'll show you 2 applications at the end. Okay, let's go ahead and clean this up. This number right here is -4. 1 minus 5, this is -4. The next one is 5, 7, 8. Down here we have 19 plus 4, that's 23. 14. Let's see, we have 24 plus 14, that is 38 minus 3, which is 35. And then the last one is 32 minus 6 is 26. There it is. Okay, so this was very complicated, but the more of these you do in your homework, the more natural it's going to be. The thing that made this work is watch. When the Roadrunner and the Coyote are multiplying, it goes like that. It just so happens that the number of columns on the first matrix has to equal the number of rows on the second matrix for that to be a nice multiplication like we did there. So you might be going, what did you just say? Watch this. This matrix has size. I usually put them above. Maybe I'll put them above here. 2 by 3. And this one has size 3 by 4. So basically, remember what I said, the number of columns on the first matrix, because we're going to go 3 this way, and we're going to go 3 down, has to equal the number of rows on the second matrix, which means these numbers have to be the same for matrix multiplication to be defined. Now here's the sweet part right here. So you're like, is there really sweet parts in this class? No, there aren't. I just made that up. But what is the size of our answer? The size of our answer is 2 by 4. And I'll write it off to the side here. 2 by 4. Do we see a 2 by 4 anywhere? Right there. 2 by 4. So that's going to give you the size of the answer. So that is the deal with matrix multiplication. It's going to be probably the most difficult part of 8.3, not the most difficult part of this class. I'm going to go back to this one here. Look at this. So I'm going to go ahead and do a size check on this. This is 3 by 2 for the first one and 3 by 2 for the second one. Look at those inside numbers. They are not equal. Therefore, it's undefined. Now, if you're kind of like going, well, I don't know, let's bring up the Roadrunner and Coyote. What happens when you multiply? You get -2, 0, Roadrunner crashes into a wall. That never happens, and it shouldn't happen. So, you know, you run out of numbers there, and then the Coyote's like, hey, I don't know if he talks, but -5 times what? And so that's what makes it undefined. And so you check that middle number, those middle numbers, and make sure they're equal. And if they are, then you can do this. So that is how you do matrix multiplication. That was the problem that we just did. I think we should do a few more matrix multiplications. Okay, and like I said, I mean, you're like, oh, when's division coming? We do not have matrix division. So let's take a look at this example right here. You know, whenever they ask you to multiply matrices in your homework, always do a size check. This one is 2 by 3. And then this one is 2 by 2. Whoa, what happened to the pen? It just started leaking. What's happening here? Okay. So the size check says, let's see if these middle numbers are the same. We don't really need to circle them to see if they're the same. They are not the same. So what is the answer? The answer is undefined. Now, let's get something straight. Undefined is reserved for expressions. Okay? So algebraic expressions, I'm not saying all of them are undefined, but it's reserved for expressions when something crazy happens, like this, or like if you have 0 on the bottom of a fraction. Because some people want to put no solution, and that would be incorrect. No solution is reserved for equations. And vice versa. Some people are solving equations that have no solution and they freak out and they write undefined equations. And then also inequalities. Or, as we have just seen, systems of equations. So if something wacky happens like 0 equals -12, then no solution. And with systems of equations, we also have the word inconsistent. But these are good things to go by. So undefined expressions that doesn't have an equal sign, no solution, we have an equal sign or an inequality sign. We can also put systems of inequalities on this list, but we're not going to do that. Let's go ahead and do problem 3. Now I want you to take a look at problem 3, how it compares to problem 2. All they did was take these two matrices and switch their order. So watch this. This is a 2 by 2 multiplied by a 2 by 3. The middle number matches. The middle numbers match, which means this can be done. Which there's a little disturbing fact at the end of this problem, but we'll go ahead and do this. Not that we're going to get undefined, but we'll say something at the end here. So let's go ahead and do the multiplication. We know our answer is then going to be a 2 by 3, which is good for planning purposes. Look, I can go like that. And when we go ahead and do this, I have, now I'm going to go a little faster on this. I'm going to have a 1 plus 8, which is, I believe, 9 last time I checked. Okay, we go back up. This is going to be negative 1 plus 4, which is 3. Okay, now we go back again. Roadrunner goes back, Coyote goes to the last column, and we have 3 minus 6, which is negative 3. Let's see if the camera's still running. Good. Now I go down here for the Roadrunner, go down to the second row, and the Coyote goes back to the first column. Negative 2 plus 12 is 10. 2 plus 6 is 8. And the last one is negative 6 minus 9, which is negative 15. So if you are in your house and your brother or roommate or sister hears the video, they're going to be thinking, what math are you in? Because all I'm saying is like 1 plus 8. That's 9, you know, and they're going to be like, wow, you must be taking like an arithmetic class. Well, you're taking pre-calculus, but we are doing arithmetic on matrices. So there is the answer. Now here's the disturbing thing that we're going to say. But look at the answer for problem 2 versus the answer for problem 3. You know, that doesn't happen with real numbers. Like if you have 7 times 3, that's 21. That's the same as 3 times 7, which means the multiplication of real numbers is commutative. But matrix multiplication is not commutative. So what does that, well, I'll write that down. Matrix multiplication is not, and I'll capitalize that like I'm shouting, is not commutative. Which means that AB does not necessarily equal BA. Sure, sometimes you can cook up some nice square matrices that will do that, and we haven't talked about it. A square matrix is a matrix where the rows equal the columns, and then this is a non-square matrix. So you could cook up an example where that could possibly work, but in general, we can't assume that will be the case. So if you go to the university and you take math classes, and they have professors who specialize in different branches of math. You might have a professor specialize in analysis, which they study calculus, but at a higher degree. And some professors will study topology and combinatorics. Some will study abstract algebra, and abstract algebra is sort of divided into 2 compartments: commutative algebra and non-commutative algebra. Non-commutative algebraist likes things like this. They like when things are not commutative, and they do research on really abstract stuff. But now if you hear the word non-commutative algebra or commutative algebra, you'll have an example of a system or a set of some defined object here, which is matrices. and how its matrix multiplication is not commutative. Let's go ahead and do another problem here. Problem number 4. And so before we do the problem, we should check. We should do a size check on here. So this size right here is 3 by 1. And this size here is 1 by 3. So we could absolutely multiply those together. And let's go ahead and see what happens with the Roadrunner and Coyote. We're going to end up with a 3 by 3 matrix. So we'll make room. And so look, the Roadrunner doesn't have very far to run, and the Coyote doesn't have very far to drop. You're just going to go 1 times 3. Okay, next one. 1 times 5. And then here goes the next one. 1 times 6. Okay, now the Coyote goes back to the first column, and the Roadrunner goes to the second row, and you go ahead and do 2 times 3. 2 times 5. 2 times 6. Okay, now Coyote goes back, Roadrunner goes down there, and you go 3 times 4. 5 times 4, 4 times 5, and you end up getting 20. And then the last one gives me 24. So that gives me the answer to problem number 4. Let's go ahead and multiply some more matrices together. Look at this example right here. All I've done is taken these two matrices and put them in the other order. And you might think, oh, it's going to be undefined, but let's see what it's going to be. This is a 1 by 3. And then this is a 3 by 1. So we have that right there. So the 3's match in the middle, so that means we can multiply these matrices together. The result is going to be a 1 by 1 matrix. So it's going to be one number there. So we have 3 plus, let me write that down, 3 plus 10 plus 24. So this is going to give us a 1 by 1 matrix 37. And I know people are so shocked, like, whoa, you can have a 1 by 1 matrix. And the answer is you've been looking at 1 by 1 matrices since the kindergarten. And kindergarten teachers might want to take a different approach. And when they start counting in the kindergarten, they should just go like this and start the kids off with 1 by 1 matrices, so that way when they reach this class, they're going to go, yes, we've been doing matrices a long time. But that was a joke, but I don't hear anybody laughing, so I guess it really wasn't a joke. So let's go ahead and do the next kind of problem. Problem number, well, we think number 6, but we're going to start off looking at these weird problems here. So we now know how to do matrix addition, matrix multiplication, subtraction, scalar multiplication. So matrices have 2 kinds of multiplication, scalar multiplication and matrix multiplication. So look what we have here. Fill in the missing number on each matrix. Okay, so for problem number 1, we're going to fill that in. I'll fill it in with blue. What would we put for that? So make sure I have my notes in the right order here. Yeah, so what would we put for this? Well, what we would put, what 2 by 2 matrix, so it's going to be a 2 by 2, would you add to this one where you would get the same thing, 1, 2, 3, 4? And you guys probably already know the answer, but I mean, we could do this with real numbers. Like, let's say you have the real number 7. What real number could you add to that where after you've added, you end up getting 7, and that real number would be 0. And so that's what's going to happen here. We're going to put zeros there for that matrix. This matrix is called, well, this right here, this 0 is the additive identity. for real numbers. So if you had like a negative 13 plus a 0, you get negative 13. So that's the additive identity. Now this is the additive identity for matrices. But we don't call it the additive identity all the time. Lots of times we just like to call it the zero matrix. Zero matrix. Okay. So now our next problem. So this was sort of introducing you to the zero matrix. A zero matrix exists for any size matrix. Okay, so for any size. So a 2 by 4 zero matrix would be a 2 by 4 matrix that has zeros on all of those 8 entries. Okay, so now this one here, what are we going to do? So let's go back over here. Is like, let's say we had 7 and we're going to multiply it by a real number to give us 7. Okay? What real number would that be? It would be 1. Now 1 is called the multiplicative identity. So really we're asking, what is the multiplicative identity for that matrix there, 1, 2, 3, 4? A lot of people would guess, so I'm writing this in pencil, 1, 1, 1, 1, which is actually incorrect, because look at this, let's multiply. We multiply, we get 1 plus 2 is 3. So we've already blown it, but it was a good guess because that was all zeros and that worked. So what we're going to do is we're going to erase some of this, but not all of it. So there are going to be ones in the corners right there, right on those corners. And what we're going to end up getting is, if you put zeros there, that will give us some results. Let's check. 1 plus 0 is 1. 0 plus 2 is 2. 3 plus 0 is 3, and 0 plus 4 is 4. So that gives us what we want. Now this is the multiplicative identity for matrices, and it's so important it's called, I'll just write it in blue, the identity. The identity matrix. And then this is going to be weird. It's only going to exist for square matrices. So only exists for square matrices. And matrices, once again, that's the plural for matrix. A square matrix, happens to be this, where the rows, number of rows, equals the number of columns. Basically, it looks like a square, and that's why it's called a square matrix. So we don't have a multiplicative identity or the identity matrix for a 2 by 4 matrix, but we do have them for these kind of matrices. Now, this identity actually has a notation. It's called I with a subscript I sub 2. So that is what the identity matrix is for that. So now, kind of, I know I'm like running off my paper here. I want to put the identity matrix for 3 by 3 matrices. And what that's going to look like is ones down this, we call that the main diagonal, and zeros everywhere else. So that's the identity for 3 by 3 matrices. And you can only imagine what the identity for 4 by 4 is. We end up having ones down the main diagonals and zeros everywhere else. So that is an introduction to the identity matrix and the zero matrix. The identity is actually really important. We're doing something called linear algebra, and that's the highest class we teach, in the highest math class we teach here at Cuesta College. Let's go ahead and do another example, because you might have something like this in your homework, and you have to, I don't want you to get confused on this. So look at this. We have matrices D, E, and F. And they ask us to do this matrix arithmetic. D times E, so this is 1, 2, negative 3, negative 4, 3, negative 1, times E, 1, 2, 1, 3, 2, 5. We have minus 2 times I2, so this is 1, 0, 0, 1, and then we have F squared. Okay, now F squared does not mean 9104. It doesn't mean square all the elements. What F squared means is F times F, in which you can only square a matrix, go F squared, if that matrix is a square matrix. Otherwise, the matrix multiplication would not be defined. You can think about that. So I'm going to write right here 2 copies of F. So I have a lot of arithmetic to do, and I suppose I should have checked this right here, because if this was undefined, that would have been game over. So let's check this right here. This is 2 by 3, and then this is 3 by 2. And so I'm going to end up getting a 3 by 3 matrix. This is a 2 by 2 times a 2 by 2, which I'm going to end up getting a 2 by 2 matrix. So this will be 2 by 2, this will be 2 by 2, that's 2 by 2. So it looks like I will be able to do the problem. I'm not going to write undefined. So let's go ahead and see if we can do this problem. Okay, so the first thing we have here is we have 1 plus 2, so 1 plus 2 is 3, minus 6, so this is going to be negative 3. Okay, the next one we have 2 plus 6, and if you want, you can go like this. I mean, off to the side, you can go 2, and I'm using the pencil here, 2 plus 6, then we have minus 15. Okay, so that's really 8 minus 15, which is negative 7. The next one, we have negative 4 plus 3. Okay, negative 4 plus 3 minus 2. So that's going to give me a negative 3. Okay. And then the last one is going to be negative 8. So maybe it's best if I had written these down here. I don't know. And then we have plus 9 minus 5. So that's going to give me a negative 4. And I did it in blue. Negative 4. Okay. So that's multiplying those two matrices together. I'm going to go ahead and I'm going to go minus. I'm going to bring the 2 in there, do the scalar multiplication. So minus 2, 0, 0, 2. And then I'm going to multiply those two matrices together. And maybe I can do that without writing the pencil. I don't know. This is going to be 3 times 3, so that's 9 plus 0. This is negative 3 minus 2. This is 0 and 0, which that's pretty easy to compute. And this is going to be 0 plus 4. Okay, so we're almost done with this. I think I can fit it on this piece of paper, and I think we could wrap this up just by doing some arithmetic. I have negative 3 minus 2, so that's negative 5. Negative 5 plus 9 is a positive 4. Okay, because that was 1 plus 2 minus 6. Okay. And then we have, let's do this one, negative 7, and then that's a 0. And then this is so we have, sorry about that, we have -7, and then the 0, and then we have a -5, so this is -12. Then we have -3 minus a 0, so -3 and then a 0, so this is -3. And then we have -4 minus a 2, so that's -6 plus 4 is -2. And so this looks like our answer. Okay, so let's go ahead and look at some applications of matrix multiplication. The first one, some of you may not appreciate, and then the second one, you might go, oh, that is a really good application. But this one, I don't know, we'll see. So remember when we did linear systems. Okay, 3 variable linear systems look like this. We had this one. In fact, we actually wrote this down as our first 3x3 system. Well, this system actually could be repackaged using matrices, where we go AX equals B, where A equals this matrix. It's a 3x3 matrix of the coefficients from the left-hand side. X, that matrix looks like variables, X, Y, Z, and B, that looks like the right-hand side coefficients. So if you're like going, whoa, what just happened here? Well, it says AX. Let's look at AX. AX is this right here. So let me write this down. And X happens to be XYZ. So look what happens when you do Roadrunner Coyote on this. Okay, so you can, because this right here is a 3x3, and this one is a 3x1. So the 3's match, and you end up getting, so this is a 3x1, you get 2x plus 3y minus 4z. 2x plus 3y minus 4z. And then the next one, you end up getting x plus 2y minus z. And then on the last one, you end up getting 3x minus y plus z. And so look what AX is. AX is this. That equals, we're looking at this right here, B, which looks like 10, 4, 8. And look, these two matrices are equal, which means 2x plus 3y minus 4z equals 10, which is exactly what we have up there. So what we'll do in linear algebra, which is not in this class, but a few classes away, is we will repackage these systems using matrices, and then we'll go ahead and throw these matrices into a computer algebra system. You know, that's what people do, you know, in cryptography or engineering. And so what we saw in our class when we solved the system, we went ahead and we took this matrix here, matrix A, and we concatenated it. That means we put this matrix A right next to matrix B, and that's how we did it. So remember when we talked about these, we have 2, 3, -4, 1, 2, -1, 3, -1, 1, and then we said equals 10, 4, 8. And we call this guy right here the augmented matrix, which was just the efficient way to solve linear systems. But really, if you took a linear algebra class, you'd see this equation a lot, and that right there is matrix multiplication, which we can see this problem right here equals that problem right there. Anyway, here's another application of matrix multiplication and why matrix multiplication is defined the way it is. So let's take a look at this right here. We've got ourselves a matrix which describes items that are sold at farmers markets. So we've got Vectorville, which is a town, and a Mathington Beach. Okay, so I made up those towns. They're mathy names. And suppose like one week, 200 apples were sold at the Vectorville Farmers Market, and 100 were sold in Mathington Beach, its location. And this is how many oranges were sold at both locations, and this is how many bananas were sold at both locations. Now, I mean, this is a simple example, and lots of companies may have hundreds of items. So you might have hundreds of rows, and then they might have like a dozen locations. So what are we doing with this? We have something called a profit matrix. And the profit matrix tells you how much profit you make every time you sell an apple, and that would be $1. And we try to simplify this example here. And then for an orange, you're making 50 cents an orange if you're that company, and 80 cents per banana. So to figure something out, so what we're going to do is we are going to multiply P times A. We are going to multiply the profit matrix times how much was sold there. And so here's $1, 50 cents, so we put that matrix there and this matrix there, and this is 1 by 3, this is 3 by 2. So we can multiply them because the inside numbers were both 3's, and then the result will be a 1 by 2. And so what do we have here? When we multiply them together, we have some dollar amounts. This actually, think about what you're doing. You're going $1 per, and you sold 200 apples in Vectorville. So that actually gives you part of your profit. So $200 you made off of apples in Vectorville, plus 50 cents per orange and 80 cents per banana. So when you add it all up, those are your profits from Vectorville, $289. And because multiplication is defined in this funky sort of way, you can actually see that it does make sense. So here is the Mathington Beach. You made $1. You're trying to compute your profit. So $1 times 100, 50 cents times 70, and 80 cents times 120, and you add them all up. That's matrix multiplication. And this number, 231, that happens to be your profits from Mathington Beach. So there is a really good application of matrix multiplication in the business world. We are finished with this section. You guys have a good day. Study hard.